Welcome to this training series on how to read a wiring diagram of an air-to-water heat pump. We read the wiring diagram from left to right and from top to bottom. At the top, we see the power specification for the heat pump. This tells us that the unit operates on a three-phase 460-volt electrical supply, which is the most common power configuration for commercial HVAC equipment in North America. You'll notice three incoming power lines labeled L1, L2, and L3, along with a ground terminal labeled PE. These represent the three hot conductors of the three-phase supply and the protective earth ground. It includes a non-fused disconnect switch, shown as QS1. From the disconnect, the three-phase power continues through terminals 1, 3, and 5, exiting on 2, 4, and 6. And then connects to the terminal block points XL1, XL2, and XL3 inside the unit. Wire size is 2 AWG. This is continuation of the same three power lines, L1, L2, and L3, running horizontally across the top. The first component connected is the phase sequence relay, labeled RCS. Its purpose is to monitor the phase order, L1, L2, L3, and ensure the rotation direction is correct. If the phases are reversed, the compressor would spin backward, which could cause severe damage. The RCS detects this and prevents the system from starting until the phase order is corrected. If any overvoltage or undervoltage issue happen at the job site, Phase Monitor will protect the unit and trip the unit. Upstream of the phase sequence relay, we have three fuses, labeled FERCs. These are small 1 amp control fuses rated for Class CC1A. 14 AWG wire used for the phase monitor. Next, the power lines feed into two identical compressors, CP1 and CP2, where 1 represents refrigerant circuit 1 and 2 represents circuit 2. Upstream of the compressor motor, unit has two identical sets of circuit breakers, QMCP1 and QMCP2, and contactors, KMCP1 and KMCP2. These circuit breakers are rated at 32 amps, and they provide both short circuit and thermal protection, preventing the compressor from overload or burnout. Right after each breaker, we see the compressor contactor, 8-gauge wire used for the compressor power wiring. Next to the compressor contactor, it is labeled that control wire for the contactor is given on page 24, column 3. Finally, notice the reference at the top right of the page, column 8. It says that the power wiring continues to page 7, column 1, where the next section of the circuit is detailed. This page continues from the same three-phase power lines, L1, L2, and L3, running horizontally across the top. 460 volt is going into the condenser fan motor. It goes through fuse, labeled FUF1. This is 15 amp class CC fuse, providing overcurrent protection for the fan motor branch circuit. The wiring from the main terminal block to the fuses uses 12 gauge wire, as shown here. Downstream of the fuses, the circuit connects to the fan contactor, labeled KMF1. This contactor acts as a high-voltage switch that energizes the fan motor when the controller calls for fan operation. The contactor coil energizes by 230 volts, which is indicated on the same page, column 8. Coil control input comes from relay output of the control board. After the condenser fan contactor, the power wire tapped off for two magnetic circuit breakers labeled QMF1A and QMF1B. Each of these breakers provides short circuit and thermal overload protection for the fan motor. They are set at 6.2 amps. The outgoing wires from each circuit breaker are 16 AWG, supplying the fan motor terminals labeled XMF1A1, XMF1A2, XMF1A3 for fan motor A, XMF1B1, XMF1B2, XMF1B3 for fan motor B. Fan motor run status wiring is landed on the terminal block XMF for both fans. Each fan motor has its own terminal markings, helping technicians identify which fan section corresponds to which wire in the field. On the far right side, we see the contactor coil circuit for KMF1, powered by 230 volt. This coil energizes when the controller or thermostat commands the fan to run, closing the contactor and supplying three-phase power to the fan motors. From column 8, it is clear that main power will continue to page 9, column 1. This page continues the wiring for fan 1 and fan 2, showing the detailed connection between the fan motors and their variable speed control modules. At the top, you can see the power connections for fan 1A and fan 1B, each supplied by three-phase power from L1, L2, and L3, along with the protective ground wire. These motors are labeled MV1A and MV1B, where MV stands for fan motor assembly. In the control board of the fan, AN1 and AN2 are analog inputs that receive a 0 to 10 volt control signal from the controller. On the lower left side, you'll see RSA and RSB terminals. These are for RS-485 communication, allowing the fan motor controller to communicate with the main system controller. Each fan also has a thermal protection sensor, shown as TV1 and TV2, wired into the control system to detect overheating and shut down the motor if needed. This page continues from the same three-phase power lines, L1, L2, and L3, running horizontally across the top. Here, we start tracing the control power circuit, which supplies 230 volts to the unit's control components, valves, and relays. The first component on this page is a control transformer, labeled TM1. It has a primary side rated at 460 volts and a secondary side rated at 230 volts, with a total power rating of 2000 VA. Upstream of the transformer, we have a primary fuse labeled FU1. It's a class CC 8 amps fuse that protects the transformer from overcurrent on the high voltage side. The transformer steps down 460 volt to 230 volt, which is then distributed through multiple secondary fuses for different control loads. These secondary fuses are labeled FU2 through FU6, each rated between 1 amp and 2 amps. The outgoing wiring from the transformer secondary to these fuses uses 16 gauge wires, while the upstream conductors from the main terminal block is 14 gauge wires. You can also see the ground connection at the transformer's secondary side, ensuring proper grounding of the low voltage circuit for safety and noise reduction. This page continues from the 230 volt control power we traced in the previous sheet. Here, we're looking at a single-phase auxiliary circuit that powers the electrical panel cabinet fan and control relays. Starting from the left, the power source is 230 volts, shown entering at the top left corner. The first device in this circuit is the control panel thermostat, labeled TE1. This thermostat is mounted inside the electrical cabinet and is typically set around 90 Fahrenheit. Its function is to monitor the cabinet's internal temperature and automatically turn on the cooling fan when the temperature exceeds that limit. When the thermostat closes, it energizes the electrical cabinet fan motor, labeled MVQ1. This is a single-phase 230 volt fan motor designed to maintain airflow within the control panel and prevent overheating of sensitive electronic components like controllers and relays. The next component shown is the phase sequence relay, labeled RCS downstream from the phase monitor. The control power continues to two relays labeled KA13 and KA12. Both are 230 volt AC coil relays, used to switch or interlock other parts of the control circuit. Each relay includes its own normally open, no, and normally closed, NC contacts, which can control different control signals or interlocks as needed. Their coil terminals, A1 and A2, are clearly shown here, indicating that both operate from the same 230V control supply. At the bottom of the diagram, we can see the relay contact diagrams for KA13 and KA12, showing how these relays control other control loops in the system. This page continues with the 230 volt control power from the previous sheet. Starting from the left, you can see the Phoenix contact terminal blocks, which serve as wiring junctions between field sensors and internal control components. The first safety devices in this circuit are the pressure switches, labeled AP1, BP1, AP2, and BP2. Each refrigerant circuit, Circuit 1 and Circuit 2, has two pressure switches. AP stands for high pressure switch. BP stands for low pressure switch. High pressure switches are normally closed switches, meaning they stay closed under normal operating conditions. If the refrigerant pressure goes too high, the switch opens the circuit to protect the compressor from damage. Low pressure switches are normally open switch. When the pressure reading is below the thresholds, it closes the contact and sends alarm signal. The wiring then leads to the contactor coils, labeled Ka1, Ka2, and Ka3, which are 230-volt AC relays. When these coils energize, they close the associated contacts shown at the bottom of the page. These contacts, in turn, enable power to flow to the compressor, or the solenoid valves. You can see that Ka1, Ka2, and Ka3 are arranged in series with the pressure switch circuits, creating a chain of interlocks that ensure the compressors only start when all safety conditions are met. Next, we have the Siemens contactors, labeled KMCP1 and KMCP2. These are the same contactors we saw earlier on the power pages, responsible for switching the main compressor motors on and off. The control signal for these contactors passes through the interlock relays shown here, ensuring that no compressor runs if the system detects abnormal pressure. To the right, we can see two solenoid valves, labeled VSL1 and VSL2. Each valve corresponds to one refrigeration circuit and is controlled by Ka10 and Ka11 relays, respectively. These are normally closed solenoid valves, meaning they remain shut until the controller energizes the relay coil. When the coil is powered, the valve opens, allowing refrigerant flow through the system. This page continues with the 230-volt control power supply and focuses on the heating protection circuits, specifically for the compressor oil heaters and the evaporator antifreeze heater, optional desuperheater heat exchanger antifreeze heater. Starting from the left, the control power feeds into the compressor oil heaters, which are labeled RCP1 and RCP2. Each compressor circuit has its own dedicated oil heater. These heaters are wired downstream of the compressor contactors KMCP1 and KMCP2, ensuring that power to the heaters is controlled together with each compressor circuit. The purpose of these oil heaters is to prevent refrigerant migration into the compressor crankcase during off cycles. When the compressor is not running, refrigerant tends to condense and mix with the oil, which can cause damage during the next startup. Each oil heater rated 66 watts, and the ground connections for both are clearly shown through the PE terminals at the bottom. Next, evaporator antifreeze heater, labeled RE. This is a 150-watt heater connected through relay Ka5, which acts as its control point. The antifreeze heater prevents ice formation on the evaporator surface during extremely low ambient conditions when the heat pump is in standby or off mode. The power wiring passes through a 3-pole connector, allowing easy field connection or disconnection during maintenance. The NO relay contact Ka5 ensures that the heater energizes only when the control logic commands it. On the right side of the page, we have another relay coil labeled Ka12. This relay controls a resistive element labeled RTD, which stands for desuperheater heat exchanger antifreeze heater. You can also see 3-pole connectors on both sides of the RTD, one for incoming power and one for the return, making it easy to service or replace these components in the field. This page continues with the 230-volt control power, and it covers the optional heating elements, the base heater and the hydraulic circuit heater. These are installed in units operating in colder climates to prevent freezing and ensure reliable startup during low ambient conditions. Starting from the left, we see the power feed labeled 1RC and 1RB, both 230V lines supplying this section. The first control device is the relay Ka7, which acts as the switch for the base heater circuit. This relay energizes when the controller detects that the ambient temperature has dropped below a certain threshold. The heater circuit downstream of this relay includes 2 base heaters, labeled RB1 and RB1A, each rated at 300 watts. These heaters are connected in parallel to provide even heat distribution across the unit's base pan, preventing the accumulation of ice and ensuring that the condensate can drain freely. There's another optional circuit, the evaporator or hydraulic circuit heater, labeled RC1. This is another 300-watt heater, designed to protect the hydronic piping or evaporator manifold from freezing when the unit is idle. It's controlled through the Ka12 relay, which energizes the heater based on temperature conditions or system mode. Both circuits are marked as optional, meaning they are included only in configurations specified for cold climate applications or customer requests. Here, we see how the 230-volt supply is stepped down to 24 volts AC using two separate transformers, TR1 and TR2, each rated at 40 VA. Starting from the top left, the circuit begins with the 230V control line feeding into transformer TR1. This transformer provides isolation and voltage reduction, converting 230 volts AC to a safer 24 volts AC, which is used for the system's control and signal components. The primary side of the transformer is protected by a fuse labeled FUTR1, rated at 0.5 amps, ensuring that any overcurrent or short on the transformer's primary side will safely disconnect power. On the secondary side of TR1, we can see two fuses, labeled FU7 and FU8, each rated at 0.5 amps. These fuses protect the low-voltage control circuits and devices powered by this transformer. The output from these fuses supplies 24V control power. We have a second identical transformer, TR2, also rated at 40 VA. It's wired the same way as TR1, with its own primary fuse, FUTR2, and secondary fuses, FU9 and FU10, each set at 0.5 amps. This page introduces the 24-volt control wiring for the motorized isolation valve, labeled V2V1. This valve is typically used in air-to-water heat pumps to turn on-off the water flow. The main control device on this page is the relay Ka8, shown near the top left. It operates on 24-volt AC and functions as a low-voltage control relay for the motorized isolation valve. When Ka8 energizes, its contacts close, sending power to the valve actuator to shift position. The relay includes two types of contacts, which is normally open, and NC contacts, labeled 11 to 12 and 11 to 14. These contacts allow the valve to be energized or de-energized based on commands from the controller. From the relay, the wiring continues through terminals XCN 16.3.5, XCN 16.3.13, which connect to the actuator terminals of the valve. Wire number that goes to the valve actuator is labeled as 55, 56, and 57. This page focuses on the power supply wiring for the Carel PCO5 Plus controller, which serves as the main brain of the air-to-water heat pump from this manufacturer. The wiring enters the controller through connector J1, with terminal G carrying the 24-volt hotline and terminal G0 serving as the neutral or common return. Wire number is labeled as 1 and 2, respectively. This page covers the digital input section of the Carel PCO5 Plus controller, which is responsible for receiving on-off signals from relays, contactors, and safety devices throughout the heat pump. At the top, we can see the 24-volt supply, labeled 16.8, feeding across multiple input channels. These 24-volt lines act as reference voltage for the controller's input terminals, allowing it to detect whether a circuit is open or closed. The first line corresponds to Ka1, a relay contact that closes when DP sensor or flow condition is satisfied. The second column connects to QMF1A, which represents the magnetic circuit breaker feedback for fan 1A. This input confirms whether the fan's breaker is in the on position. When the breaker trips or is manually opened, the input goes low, and the controller recognizes a fault condition. Next, we have the contact from Ka13, which is tied to phase monitor. Following that, we see QMCP1, which is the compressor 1 circuit breaker feedback. Similar to the fan breaker input, it signals whether the compressor protection is intact or tripped. When this breaker is open, the PCO5 immediately disables compressor operation and logs an alarm. The remaining two columns show Ka2 and Ka3, which are the safety interlock relays for Circuit 1 low-pressure switch and Circuit 2 high-pressure switch. The 24-volt common return is shown at the far right, connected at J5. IDC1 terminal and completing the input loop and returning to the transformer ground reference. This page continues from the previous digital input diagram. At the top, we again see the 24-volt supply, labeled 19.8, running across the top of the page. This low-voltage feed powers all digital input channels, allowing the controller to detect open or closed states from safety devices and interlocks. The first input column on the left includes a set point selection switch, shown as 2-degree set. This field wiring option allows the user to toggle between two operating set points. For example, a normal mode cooling set point and an energy-saving mode, or comfort and night operation set point. Next, we have the QMCP2 feedback, which is the compressor 2 circuit breaker signal. This input lets the controller confirm that the second compressor's breaker is switched on and that the protection circuit is intact. The third column represents QMF1B, which is the fan circuit breaker for the second fan motor. This page continues the digital input section of the Carel PC05 controller. The first vertical line represents a relay contact labeled KA4 for circuit 2 high pressure switch. The second column represents the thermal protection feedback status for the evaporator or chilled water loop circulation pump, labeled MTP1. This is field wiring option. If you wanted to control the pump, installed external to the heat pump, the feedback status wire will be landed here. The terminal block is labeled as XC, and terminal point is XC7 and XC8. This page introduces the digital output section of the Carel PC05 Plus controller. Unlike analog outputs that send variable signals, digital outputs act as on-off commands, energizing relays or contactors to start and stop field devices such as pumps, valves, or fans. At the top, we see the 230-volt power supply, which provides voltage to the relay output block. D12-1001 represents the evaporator pump 1 control circuit, manages the operation of the primary evaporator circulation pump in the system. The relay output J12.N02, which energizes the KA1 relay coil for the compressor contactor coil for circuit 1, KMCP1. You can see another relay coil labeled KA8 at the relay terminal J12.N03 for opening or closing the motorized isolation valve at evaporator. This page continues the digital output section of the Carel PC05 controller. At the top, we see the 230-volt AC power supply feeding into the controller's relay output block. When the PC05 energizes the output at J13.N05, the relay contact closes, sending 230-volt power through the XCN10.4.1 to XCN10.4.6 terminal block contacts, energizing the solenoid coil. The valve opens, allowing refrigerant flow, and closes when de-energized, ensuring precise control of refrigerant routing within the heat pump system. Next, J13.N06, we see Vice 1, labeled as the reverse cycle valve for circuit 1. This valve determines the operational mode of the heat pump, switching between heating and cooling. When the valve coil is energized, it changes the refrigerant flow direction by reversing the high and low sides of the circuit, effectively switching the condenser and evaporator roles. When de-energized, it reverts to its default mode, usually cooling. The reverse cycle valve coil receives power through relay contact KA1, shown in series with the output line. This ensures that the valve can only operate when the system is in the proper control state, protecting the compressors from switching under load or at incorrect conditions. This page continues under PC05 digital output section, showing J14.N07 and J15.N08 manages two key functions, fan control and hardwire connection for alarm signal of the heat pump. The relay output J14.N07 energizing KA13, a relay, which in turn drives the condenser fan contactor, labeled KMF1 tile. The general alarm output is at J15.N08, and field wiring terminal for that is XC19XC20 for normally open contact. There's also an important note on this page, max 50 volt, which specifies the electrical limitation of the alarm contacts. At the top of the page, we see the 230-volt AC supply feeding into the controller's relay output bank, identified as J16. In this diagram, the relay output J16.N09 is connected through relay KA3. When the controller detects a demand for cooling or heating from refrigeration circuit 2, it energizes KA3, closing its contacts and completing the circuit to KMCP2, the compressor 2 contactor coil. The contactor KMCP2, shown near the bottom of the page, operates on 230V AC and serves as the primary control point for the second compressor motor. When energized, it closes its 3 power contacts, allowing full 3-phase voltage to reach the compressor motor terminals. At the top, the 230-volt AC supply powers the relay outputs in 2 separate blocks. J17-NO12 energizes the VSL2 solenoid valve relay coil, which controls refrigerant flow in circuit 2. It's wired through terminal connections XCN 10.4.2 to XCN 10.4.7. The coil energizes, opening the valve, which allows refrigerant to flow through the circuit for hot gas injection. On the right side, at J18-NO13, we see KA7, a 230-volt relay coil, optional base heater for the heat pump. We're now looking at another PCO5 digital output page. On the left-hand side of the schematic, we see the control for the reverse cycle valve VIC2, which manages the refrigerant flow direction to switch the unit between heating and cooling modes for circuit 2. The 230-volt supply feeds a set of relay outputs at J21 terminal block. From there, the circuit continues through KA3, a relay coil for high-pressure switch that acts as the interface between relay output and the R-versing valve coil. When KA3 is energized, it closes its contacts between terminals 31 and 34, allowing voltage to pass through terminals XCN 16.1.6 to XCN 16.1.14, energizing the VIC2 reversing valve coil. Now moving to the right side of the page, we see KA10, another 230-volt relay controlling the solenoid bypass valve, labeled VSB1 for refrigerant circuit 1. This valve allows refrigerant to bypass certain parts of the circuit during specific operating conditions, such as defrost mode, low load operation, or system equalization. When KA10 closes, voltage is sent through terminals XCN 10.4.3 to XCN 10.4.8, energizing the VSB1 solenoid bypass valve coil. This page continues the PCO5 digital output section, detailing how the PCO5 send on-off signal to relay coil, KA11 for solenoid bypass valve, VSB2, at refrigerant circuit 2, relay coil, KA5, for the evaporator heat exchanger antifreeze heater and hot water side pump, on-off command to pump 230-volt relay coil. The pump command is field-wired option and should be landed at the terminal XC22, XC23. When VSB2's coil is energized, the valve opens, allowing bypass flow through the refrigerant circuit. This page shows the communication interface wiring for the Carel PCO5 controller. Here, we see a small communication block labeled J23, which includes 3 terminals: TX, transmit, RX, receive, GND, signal ground. These are standard serial communication lines used for RS-485 communication. This is communication between PCO5 and expansion valve driver.